So, welcome back. Hope you enjoy lunch. So, this section I will talk about Tractable reasoning service for semantic MediaWiki. I'm Jeff Pan from the University of Aberdeen. So, this is John's work together with my PhD student Jack. So, the tool that we talk about is called TrOWL. Sometimes people also call it TrOWL. So TrOWL is a reasoning infrastructure for OWL2, the second version of OWL. So yesterday in Marcus' keynote, he talked about intelligence applications. So I say reasoning services would be useful support for building intelligence applications in SMW. So because this is a user conference, basically don't expect too much technical details. So basically what I would like to do is to talk a little bit about motivation. Why do you need to do this and why do you need to do that? So obviously, I would like to talk about why do we want to do reasoning, or put it in another way, can we avoid reasoning at all? I mean, what kind of price do we need to pay if we want to avoid reasoning? And then I will introduce some of the techniques that we use in the TrOWL infrastructure. Because time is really limited, I will mainly focus on the faithful approximation techniques that we have published in these few years. We won't have time to talk about divide and conquer technologies, but that will be very important as well. And then we'll talk about how do we use TrOWL with SMW, and hopefully my demo works. So, why reasoning? Obviously, I think in the semantic web these days, people care about data. But obviously, there are two types of data. The data that you have in your TrOWL store. So they are the explicit data. There's also some implicit data that they are not explicitly stored in the TrOWL store. However, when we want to query, or when data consumers want to query the data, they would not just want to query against the explicit data. They also would like to query the implicit data. And reasoning could help. So in what follows, basically I will give two examples to illustrate what I mean by implicit data. And in the first setting, basically it's in a centralized environment, so you have a central ontology and data. And then in the second case, basically you have different data sets, and you can use techniques like what Andrea and Michael talked about. You can identify links and do something about them. So the first example, like you have a wiki page about United Kingdom. Well, obviously, if we use semantic MediaWiki, it would be even better because we could actually add some semantic annotations or ontological annotations to some of the terms, like UK, we know that it is a country, and then we know that United Kingdom is located in Europe, for example. Well, obviously this is something that you could do in SMW, but you might find it difficult to get it done in usual wiki. So how this is done? Usually you basically have some data annotated with vocabulary defining ontologies. So you have United Kingdom as a country, and United Kingdom located in Europe, and then you have some queries. Obviously you're using some SMW format to write a query, but the query can be easily written into Sparkle. So the query we're talking about here is we would like to get some country that's located in Europe. Obviously, for our example, we have only one answer. That's the United Kingdom. So the real example starts from the next slide. So suppose we would like to actually enrich our wiki page with something that we have in another page, where you can see actually, well, it's not very clear here, but I could read it from here. So it's United Kingdom is also known as UK or Britain, right? So, and then now you have a new statement adding into your data set saying Britain is the same as United Kingdom. Now, if you start to do the same query again, like what we did in the previous slide, you only get the answer of United Kingdom if you do not do reasoning, because you would like to get countries located in Europe, and only United Kingdom is explicitly stated that it is a country located in Europe, but Britain is not explicitly mentioned in this way. So reasoning is important for you to actually find out connections, find out all the implicit connections across your data and schema. So this is the first example in the local setting. The second example actually is something that we used in this year's Reasoning Lab Summer School. Aidan Hogan gave a talk together with me on large-scale reasoning for linked data. So the example is actually taken from Aidan's part. I quite like it. So in the web, you can see many different URI about the same resource. You can use many tools, for example, to find them out and connect them. Well, the same problem appears, right? I mean, in our previous example, we only have one very simple data set. We only have, United Kingdom located in Europe, so just one triple. But in many of these sources, there are hundreds, if not thousands, of triples associated with each one of them. So when you want to query, for example, a web page related to Tim Berners-Lee, basically, if you don't consider the connections, you only get the local ones. So obviously, if you want to avoid reasoning, there are several approaches. The first approach is to just email the publishers and tell them to write data with all possible combinations. Copy and paste the data across all the equivalent URIs. For example, you could write email to Tim and ask him to actually add all those triples into his file file and potentially add further new URIs there as well, so that make it easier for people to use their data set. So this is obviously one way, but people might not like it. Another way is actually to tell the users to ask the right query. So we always complain to the user that, well, you're not asking the right question. If you ask the right question, I'll tell you all the answers. So to do that, basically you could ask them to union many different things on top of the basic full page and page. Obviously, the users need to find out all these other things related that we want. So what I'm trying to say is that of course we could avoid doing reasoning, but we might need to pay a price that not many people might be comfortable with it. So if you really want to make our publisher happy and the users happy, at the end of the day, it might be an idea to use reasoning support, which could provide some automatic computation to get the answers that you want. So as I said, in linked data, basically people could use a vocabulary to annotate the data, and the vocabularies are usually defined in ontologies. There is a standard ontology language called TrOWL, and in the year of 2009, basically there is the second version of our standardized. So one of the major different things from R1 and R2 is that in R2, well, on the one hand, you have more expressive power. For example, you could actually use R2 to cover a lot of rules that you would like to express. So, for example, Marcus has done quite interesting work on that side. But on the other hand, actually, you could actually have some tractable fragments, tractable in terms of computational complexity, with p-type complete or even less complexity to do reasoning. Interestingly, none of the three tractable profiles are subset of the first version of R. So there's some very interesting new things in R1 and R2. So how does it relate to TrOWL? So basically in TrOWL we have reasoners for some of these profiles, in particular out to EL and out to QL. EL is mainly for T-box and A-box reasoning, and QL is mainly for query answering. Obviously, having this tractable profile will be very helpful for users, but sometimes people find it confusing as well, because they're not logicians. They find it difficult to understand what are the differences between all these languages. And they don't know the trade-off. They have something to model, but they don't know what to drop or what to add to be inside these profiles. So one thing that TrOWL allows you to is to actually use the most expressive decidable language in the framework, which is out to EL. And then depending on the reasoning service that you use, TrOWL will actually automatically pick up some approximation techniques to approximate your ontology into ontologies in these profiles, which means that the users do not have to worry about which sub-languages which. You can always use, for example, some ontology editors like Polisher, Toolkit, Neon Toolkit, and some nice tools from other points to design your ontology, and then you use reasoning service. So as I said, we have basically two major steps to achieve. The first step is to provide really responsive reasoning service. So you don't really want users to wait. In many of the situations, and many of the one in our most project, marrying ontologies and software technology, basically you need to provide reasoning service within 2 seconds. And so you have to come up with responsive reasoning service. And when the data set is so large, that one single node is not able to deal with, so you start to consider divide and conquer technology, like parallel reasoning, distributed reasoning, or other techniques like modernization, etc. So here I just talk about the faithful approximation techniques that we published in 2010. So the idea is based on the following observation. If you look at out to EL, and look at a large subset of it called log, or out to EL, a large subset of it is EL++. You can see that they actually share most of the constructors, and the only two things in terms of concept, which is in log but not in EL++, is the full negation and the qualified number restriction. Now, one idea for us is to find some syntactic manipulation to fill the gap between these two, so as that you could actually use EL++-like algorithm to do reasoning with out to EL. We did some experiments in the beginning. The idea is simple. We just simply drop all the axioms which are not in out to EL from the ontology. What happens? For some of the ontologies, it performs really well. I mean, obviously it's very efficient. But for some of the other ontologies, the completeness the recall is very low. For example, for a cycle ontology, if you drop all the axioms that are not supported by out to EL, then the recall is only 1%. So you lose a lot of reasoning. You lose a lot of connections that you could find for your data set. So at the end of the day, in the paper, basically our approach is not to throw away anything. So basically, whenever we have something that's not supported by out to EL, we introduce a fresh concept name to represent that expression, and then we introduce some data structure and additional completion rules to recover the hidden semantics within these fresh names. I'm not too sure if I have time to give an example. If I have time at the end, I could give an example to show actually how to actually use EL-like algorithm to do reasoning with EL. So now I could give you a short demo. Yeah, to save time, basically I actually have done the first part of the reasoning already. So we compare that against one of the well-known reasoners here. The ontology that we use is quite a challenging one. It's called ELP 397. it is a version of the Apple ontology called TrOWL. So it is trilogy because there are a lot of property axioms within the ontology. If you use this sign-complete reasoner to do the classification, it takes about 70 seconds, 69 seconds. So if you use our approximation-based reasoner to do reasoning with the same ontology, so that's P397. It's done in less than 1 second. So you see the difference, and the reasoning result is the same. We also tried some of our project ontologies. So the following one is actually an ontology related to access control. It can be done in less than 0.1 seconds, but if you use some sign-complete reasoner to classify the same ontology, you can see that at some point, it just stopped there, and as far as I remember, it won't stop until 12 hours. So this is just some example. So what about more general evaluation? Basically, we've done some evaluation using the Oxford benchmark for their Hermit reasoner. So there are about 100 ontologies and about 20 to 30 difficult ones among them. So we compared the performance between our approximation-based reasoner, TrOWL, against some well-known reasoners like Z++, Hermit, and Pilot. So we look at the time performance in terms of seconds, and also we look at the recall of the approximation-based reasoner. You can see that actually TrOWL is actually quicker than all the other sign-complete reasoners for all of the ontologies. And for some of the difficult ontologies, like the FMA ontology, all the sign-complete reasoners cannot finish within 10 minutes, while TrOWL was finished in 10 seconds. In terms of recall, surprisingly, actually, TrOWL is very complete. So in 2010, basically, TrOWL is complete for, the recall is 100% for all the ontologies in the benchmark, except the one ontology, which is the benchmark ontology in our working group, which consists of every single constructor in the language. But this year we fixed the problem, even for one, and it's 100% as well. So this is another approach that we did. So this is not based on syntactic approximation. This is based on semantic approximation. So it's for QL, query answering. I don't have time to give the details here, but looking at state-of-the-art reasoners, if you use K12 or Razor or Pilot, according to Boris Montek's evaluation in 2006, basically these ontologies could deal with up to 4 universities in the Neha University benchmark. For other approximation systems, they are much more scalable. Easily deal with 50 or even 100 ontologies. However, there's no sum or completeness guarantee for those approximation-based reasoning service. So in 2007, we published this semantic approximation approach and implemented in our reasoner called QL. So QL is our QL reasoner with semantic approximation support. You can see the performance against other approximation systems like ELDB. So when you have a small data set, the two systems performed similarly. When you have a slightly bigger data set, you can see QL is at least 100 times quicker than ELDB. The main advantage for QL comes from the fact that QL actually has very low data complexity. So getting back to the big picture, TrOWL is actually a reasoning infrastructure. It's not just containing one or two reasoners. We have quite a number of reasoners, and it supports our API compatible reasoners. You can use it with Protege 4. You can use it with Journal and semantic video. I'll get to that one in a minute. It's quite configurable as well. You can actually use some feature modeling to specify what kind of expressive powers that you use. Actually, it could configure the best, define the best reasoner for you as well. So I'll just talk about approximate questions.
Yeah, just a quick one. The REL and QUIL and so on. Are you developing those, or is that external?
My students develop them.
Okay.
Yeah. So I just talked about approximation service like REL and QUIL, and there are other work on divide and conquer, which is very promising as well. So the idea is that we would like to make sure one computation node is very efficient and responsive, and then we can have multiple, one node with multiple workers or even multiple nodes to work together to achieve scalable. One interesting feature that people like very much is the so-called local closed-word reasoning with negation as variables, in which the users could actually specify the list of concepts they have complete knowledge about and leave the other concepts open. So in our next release, we will come up with string reasoning as well, and we've got some recent publications for that. So without further delay, you might ask, how do I use TrOWL together with SMW? Well, the idea is simple. Basically, you could use the Sparkle extension. If you're able to use Sparkle extension and you're able to use Joseki, then pretty much you could use TrOWL already. So most precisely, you need to specify the highlighted part in your configuration to say that you're using the TrOWL journal factory as a reasoner class. So I'd like to give some demos. So basically, that's something that we maintain in our server. So here we have 4 queries. So all about the wine ontology. So the first query is about looking for wine that has strong flavor and joy from New Zealand. The second one is again some wine with strong flavor. The third one is about some blank white wines, and the fourth one is about some dessert wine from Germany region. So as you can see, you could in your wiki page you can write down queries like this, and you go to when you go to the page, basically you will retrieve the result from your Sparkle S model. You can see that you have 2 answers for the first query, 9 answers for the second query, and none answer for the last 2 queries. Hopefully, so the next one we want to see is the on-the-fly reasoning thing. So, which means that you actually do reasoning for that. Yeah, it's quite quick because on one hand, the reasoner is quite efficient. On the other hand, basically you could set it up in such a way that if in the same day other people visit the same page already, it is cached. So you could see that if you do reasoning, in query 1 you still have 2 answers, which means that you don't need to do any reasoning to get all the answers for query 1. For query 2, and you have 11 answers altogether, so which means that if you don't do any reasoning, you will miss 2 answers for the second query. For query 3 and query 4, it turns out that there are some answers for that, but if you don't do reasoning, you miss all the answers. You miss all the nice dessert wine from Germany, for example, which is not good, I think. And so, so this is just on the slide, and you could also, I mean, it's not difficult for you at all to actually materialize the reasoning result and so store it back to your Sparkle endpoint or the data set, so that you don't have to do reasoning every time. So if you're able to do reasoning on the slide, you're able to do, it's not difficult for you to store the data reasoning result there as well. So, yeah, the demo seems to be working. So, yeah, the conclusion. Well, when I talk to people, I mean, many people work on the field of linked data. They always have this, I think, illusion that using linked data principle could help you integrate the data. But this is not. It's not the case. Linked data principle help you to make the data linkable and shareable. That's it. In order to integrate data, you need to do at least 2 extra tasks. One is you need to find out the links, like what Annie talked about this morning. And then once you have these links, you need to propagate all these connections using reasoner. So in order to do integration with linked data, having the principles are not enough. You need to do 2 more tasks. And obviously, we would like to have Tractable and scalable reasoning service to finish the second task. As I explained, TrOWL or TrOWL is a Tractable reasoning service, reasoning infrastructure for L2. It actually exploits the feature of L2 in such a way that on the one hand, it supports all the Tractable fragments, and on the other hand, it allows you to use the same level of service but with more expressive ontologies. As you could see, it's not difficult to use it together with SMW. As long as you could use it with DDB and Jasaki, you just need to change one line of your configuration file. You could just put the jar file of the TrOWL into some of the folder, and that's it. TrOWL is actually open source. There is also some version which is not open source if you prefer that way as well. There is a related book that we edited recently. Well, we're finalizing the book with Springer actually, so it is about ontology-driven software development. I think semantic mini-wiki could play a good role in the software development lifecycle with semantic technologies as well. And also, if you think about some further following up events about semantic web and semantic mini-wiki, so there is a conference in December this year called JIST, John International Semantic Technology Conference. So it is a John event. So basically this is a international conference to promote regional semantic web conference. So this year, JIST 2011 is a joint event between the Asia Semantic Web Conference and the China's Semantic Web Conference. So Ian, Tractable, and John Weiss are the general chairs, and I'm one of the peace program chair of the conference. And there will be a keynote by Mark about, I think, about semantic mini-wiki, and also Jesse will be kindly giving some tutorials about SMW as well. Furthermore demos or live stream talk about SMW are very welcome. So it will be in a very beautiful city in China, Hangzhou. I mean, as far as I know, that's the most beautiful city in China. And it's only about 40 minutes away from Shanghai if you go for one of the high-speed train service. And here's the website, you can find out more information about it. So, thank you very much. hopefully I've convinced you that reasoning is important and useful, and TrOWL will help you to find out more answers of your queries as well. Thank you. Any questions?
Thank you. So if I understand your architecture correctly, what you do is you have a module to the TrIPL store based on Jenna, which transparently will do reasoning whenever a Sparkle query is executed to augment the results accordingly. So this immediately also implies that the new TrIPL store connection features that SMW has, as far as they connect to Jenna in the first place, would also work with the same architecture. So if you don't use Sparkle extension, you could also just directly connect to Jenna and use your tool.
Yes, yeah, you're right. So basically, this connection is enabled by our support for Jenna. So if you have other extensions that using Jenna, that will work as well. Yeah.
So you talk to the Jenna API.
Yeah. So we use Jenna API to support this kind of communication.
Did someone try Jenna with the RDF store binding of SMW yet? Does anybody know if Jenna is working with the
No, you've seen it already.
No, but that was with the Sparkle extension.
Oh, right, okay. We
so
downloaded Sparkle extension. I don't know. We use, yeah.
Since version 1.6, SMW has the option to connect to a TrIPL store natively, to store its native data there and to format it in the way you would normally see it in the wiki, so you don't see the URLs. It just directly has the data there. And so together with this, it could be quite interesting to do reasoning on
So you mean we downloaded the Sparkle extension?
Yeah, so it's not pulling in external data via Sparkle, but it's using Sparkle on your own wiki data to answer the asked queries. And you could still use this tool, for example, to
yeah, that would be interesting. Yeah, we could talk to you to see how to use the new thing.
Probably, I hope it works. If Jenna supports Sparkle 1.1, it should work.
I think.
Basically, directly following up, if you apply reasoning to data you are maintaining on the wiki, you may run into the problem of inconsistencies because it's very easy to introduce inconsistencies. Do you have any mechanism to deal with that, or will usually if you have an inconsistency in your ontology, reasoning will simply fail?
Yeah, we do. I mean, I could give you a demo as well. Unfortunately, someone has just disconnected my laptop.
Yeah.
Doesn't matter. I could believe me. I can. So basically, yeah, we could have justification for every inconsistent class or inconsistent ontology. You compute the justification, which means that that's the minimal subset of the ontology that cause the reasoning with some reasoning result or cause the inconsistency. Yeah.
Okay, so you could locate the problem.
You could locate the problem, yes. Which means that you could do debugging accordingly. Yeah.
I don't know if anybody has asked that already, but what language is it written? Java or?
You mean TrOWL?
The REL.
Yeah. Oh, that's part of TrOWL. Yes, Java. Everything is in Java. Yeah, Jenna is in Java as well.
REL is not TrOWL?
REL is a reasoner in TrOWL. There are many other reasoners.
Okay.
Yeah. So the idea is that, when you have an ontology coming in, and the more complicated the ontology is, what we try to do is we do not use all the inference rules for all ontologies, because that will slow things down, because you need to maintain some extra data structure that's not useful for your ontology. So what we do instead is that we track the expressive power and we load the inference rules accordingly.
Okay, so dynamically
changing. So REL is just one instance of the reasoning that we have. We have many others. Yeah.
I understand you also support FuzzyJS.
Hey?
FuzzyJS you also support.
Support.
So something like FuzzyLogic supports Azure Group. So there's a fuzzy version of the yes rule.
Sorry, I didn't quite get the question.
You support yes, don't you?
Yes.
I probably don't pronounce it very well. GESS.
JES.
Yeah, JES. Yeah, that's the reason. It's a rule engine.
Yes, that's another rule engine.
You support it?
Uh,
I thought so, I thought I saw.
no, it's Drena. We support Drena.
Yeah,
And
there's
Polish.
There's a triple store which you do support quite a few reasons, rule engines, don't you?
Well, Jazz is it's a rule engine, so you could connect that with TrOWL, but I don't think we've looked into that already.
Okay.
Yeah. Okay. Thanks. So I think without further delay, we should hand over to the next speaker.